To this week's CDAR seminar. I'm Lisa Goldberg, one of CDAR's co-directors, and it is my pleasure and privilege to introduce someone that you probably all know, Baeho Kim, who visits us. We are so fortunate, visits us often and for long periods and collaborates here at Berkeley, is an integral part of the CDAR community, talking about a subject we've all been working on for at least a decade, which is how to forecast financial risk, I guess. So long-history PCA under dynamic factor model and weak points.
Thank you, Lisa. Thank you very much for having me once again here. And thank you so much for joining my presentation. My talk for today will be about the estimation of dynamic factor model with potentially weak loadings by PCA estimation under the long history of data. My understanding is that an earlier version of this work was presented at this seminar series previously. So my talk for today will be primarily focusing on the extended part with the new findings mostly, but still is in progress. So as Lisa said, please interrupt me as frequently as possible if you have any comments, questions, suggestions. That will be highly appreciated. This is a joint work with Professor Robert Anderson and Mr. Donghan at Oxford. So before I jump into the details, let me first clarify what we actually mean by the risk in this study. It's been said that there are two different orders of the financial risk, namely first order risk versus the second order risk. Basically, the first order risk refers to the variability under the completely known risk profile or the complete perfectly estimated distribution, so that one can certainly evaluate the risk-return trade-off under the completely known distribution information set. On the other hand, the second order risk may arise when the risk profile is not fully understood or potentially misestimated. So the risk-return trade-off, risk-return relationship is unclear. For example, the Shepard in his 2009 paper introduced the concept of the second order risk by saying that the real financial markets do not behave like a game of chess under the completely known distribution, because our estimates of the financial risk are more or less uncertain based on the limited historical observation potentially extrapolated forward. So he also stressed the practical importance of this notion of the second order risk by saying that managing a portfolio to a risk model can tilt the portfolio towards the weakness of the model. This is the mechanism of so-called error maximization sometimes, right, under the subject to the second order risk. And this is the notion that we follow. And also
that tilt will occur particularly regularly if markets are efficient, because markets will offer a lower price than the misspecification will indicate, because markets will perceive the risk, the secondary risk, and price it in.
I'm very happy that you mentioned that. I will show you some empirical evidence, something related to your point. Thank you very much for saying that. And also, this notion of secondary risk is also related to the distinction between volatility and uncertainty, which is another hot topic in the recent asset pricing finance literature. For example, Salia and his co-authors published a paper this year, 2024. This is a brand new paper, investigating the implications for asset pricing and portfolio performance when uncertainty and volatility are disconnected. According to their definition, volatility measures the dispersion of the short-term shocks, whereas the uncertainty measures the difficulty to forecast the distribution of the returns. And also, this concept, second order risk concept, is maybe partially related to the concept of the ambiguity back in 1961. What the Daniel Ellsberg claimed was that people tend to prefer the quantifiable risk to incalculable or the unquantifiable risk, which he called ambiguity. And recently, Brenner and Ezekiel in their 2018 JP paper, they showed that the ambiguity premium is indeed very strongly priced in the equity market, even after controlling for the traditional risk premium effect. And they argue that the ambiguity premium can be a partial solution to the equity premium puzzle. Statistically speaking, this secondary risk may be quantified by looking at the standard error of the standard deviation product, whereas the standard deviation itself quantifies the degree of first order risk, I think. And in terms of the source of the secondary risk, it may come from either the potential misspecification of the model or the miscalibration of the model or both. So basically, this is, I mean, as highlighted in red, the secondary risk is where our motivation comes in. But basically, this is such a big question to be addressed by just one paper. So we kind of narrow down the scope of our research by revisiting the classical mean-variance framework of the Marquis portfolio optimization. What's happening here in terms of the secondary risk issues is that the out-of-sample performance of the optimized portfolio is known to be extremely sensitive to the parameter estimates. Basically, we have two parameters to estimate. One as the vector of expected return mu and the sigma as the covariance matrix. What's happening again is that the small errors in the estimates of these values may substantially misrepresent the efficient allocations, and that's what the Shepard actually says the tilting the portfolio towards the weakness of the model. At this moment, I have to say that our primary focus in this study lies within the estimation of the sigma covariance matrix and its inverse matrix, which is called precision matrix. And we don't examine whether the risk vectors are priced by dropping the constraints there, crossing red. I'm not saying that the estimation of mu is not important. It's as important as the estimation of the sigma covariance matrix, but it's just out of scope of this research and it's left for the future research. But maybe we can say that the significance of the estimation error on mu may become less important in the short-term horizon optimization, say daily pricing. But at least we can still say that the mitigating the estimation error of the covariance matrix and its inverse matrix is still very important and essential for determining the admissible portfolio compositions within a given risk budget. The issue is the estimation. I mean, the estimation of the covariance matrix becomes more challenging, especially when the dimension n of the population covariance matrix becomes larger and larger, because the estimation based on the history observation is limited, right? It's challenging. Perhaps one of the most popular approach is the principal component analysis, PCA, which is effective for predicting the short-term risk. What's happening in practice is that the most practitioners are unwilling to run the PCA over data histories longer than 1 or 2 years for large portfolios. So in most of the cases, the number of observations T is way smaller than the size of the population N. There's one exception, Northfield, which uses a hybrid model of the fundamental vector approach and the PCA approach on the residuals. But based on my understanding, they are using those 60 months of the monthly data. So their T is still 60, so usually it's still way less than N. So when T is less than N, what's known is that the estimated model is significantly contaminated by so-called finite-sample error. So briefly speaking, if we naively and simply estimate the covariance matrix based on the statistically estimated sample covariance matrix, especially when N is larger than T, that estimated sample covariance matrix becomes singular, and its inverse matrix is not well defined mathematically. So the constructed optimized portfolio, its performance becomes totally impractical, maybe, okay? Especially when N is way less than T. When one popular way to correct this bias is a shrink estimates the sample covariance matrix. It's suggested by, for example, Ludo and Wolf 2004, and this is one of our important benchmarks. But to my knowledge, the vast majority of the commercially available vector approaches, commercially available approaches are based on the PCA estimation of the linear vector models. As I said, many of them are trying to estimate the vector model by PCA using a median data history of TM, say 1 or 2 years of the history, to stay within the static nature of the vector model. Okay? They have to be, I mean, they need some, for the consistency of the PCA estimates, they typically assume the steady nature of the vector model assumption. So because of that, they're using TM, the median history of the data set. Usually using the vector model is known to much better handle the finite sample error overall to figure out the structure of the vector model. But it's known that the estimated vector loadings, okay, is still highly inaccurate when n is way larger than t. And it's known to produce so-called access dispersion bias in the sense that the estimated vector loadings they appear to be more dispersed than they appear. One way to correct this bias within the steady nature of the vector model approach is, I think, the GPS correction, which I like very much. But here we have Lisa Goldberg. Goldberg and her two co-authors published a 2022 paper suggesting that this access dispersion bias can be effectively corrected by correcting the leading eigenvector estimated based on the PCA. And they show that their correction can asymptotically eliminate the source of the bias under the large N and fixed T horizon. But there are still most of the approaches, commercially available approaches, are within the steady nature of the covariance matrix or the steady nature of the vector model approaches. So to overcome this issue, in reality, of course, the vector structure is well known to rapidly change its shape over time. So to address this issue, most of the commercially available vector models typically use so-called two-history algorithm. I'm saying is that in the first stage, a variant of the PCA over medium data history, say 1 or 2 years, are used to estimate the vector loadings, and they may apply some bias correction method to correct the bias. And then in the second stage, they employ some time series model like the exponentially weighted moving average volatility model, with a short half-life like 30 days or 40 days, to estimate the current vector structure.
Which are the commercially available models that do this? Because the ones that I know mostly don't use PCA at all.
What I'm saying is that they use kind of 2 different steps. Okay, first they try to figure out the vector structure. Okay, what I'm highlighting here is that they tend to use a shorter history, not like the 5 years or the 10 years of the history to figure out the vector structure.
Because just do you mean the bar model here? Because I'm not sure it works exactly that way.
I'm eager to learn the details.
Yeah. Okay. So we can talk.
Okay.
So
I think the issue is a variant of PCA, so mostly these would be fundamental factor models.
Yeah.
And then if you put in a fundamental factor model in the first bullet, then I think this is still correct, right? Because bar wouldn't just take the estimated factor, the estimated fundamental factors, it would also apply a correction based on recent volatility of the factors. Yeah, it does. It does.
But bar doesn't use any PC.
It doesn't use PCA, but if you take a variant of PCA and replace it by fundamental factor model, I think that wording is not accurate.
Okay, I'm just trying to understand. I'm not criticizing at all, but I'm happy to tell you how the bar models work and the BlackRock models work. I do know that Bloomberg, which is doing, Jose's been here, is doing something a little bit different, and it is totally using PCA.
Okay.
But the bar models, I think it doesn't have anything to do with the development of your talk. I use PCA models personally all the time. I like them.
Thank you for pointing that.
But I just want to just check that we have a common understanding of what the commercially used factor models, for better or worse, actually do.
Okay.
Would you agree they use a 2-history model?
The 2-history model, I think that if one of the histories has length exactly 1 day, then I would agree the answer is yes.
Okay.
But we can
Yeah.
talk, but it is literally 1 day. And it's quite clever. And I can explain how it works, but it is a little bit different than this. But anyway, it doesn't make in any way diminish this, and we should just come to understand it. Make sure I know what I'm talking about.
For providing the information, but we basically stay within the nature of the PCA estimation.
Which is
word.
It is a fantastic,
Right.
and for good
Yeah.
reason. Because
I'm
as you
still
say, the
trying
factors.
to motivate our
Yeah.
approach. So the thing is that I want to mention at this point is that we empirically observe based on our empirical data set that the variance of this type of approach with the median data history, like 1 or 2 years,
Yes,
suffer from a significant amount of the SOR, secondary risk bias. It depends on which measure we take, but this is the first point that I want to mention before we jump into the details for our approaches.
got it.
Thank you very much. And here's the statement of our objective clearly. Our objective is to evaluate and mitigate the second order risks which may originate from a dynamic vector model at a very large portfolio level by extending P. So we take a different approach. So we try to extend the P, but of course, there's a number of costs that we have to pay to take this approach. I'm going to focus on some practical challenges in the next slide. But anyways, more specifically, we try to accurately forecast the population covariance matrix in the precision matrix, which may be time varying. At a fairly large stock returns more than 2,000 on a short term, say daily basis within so-called long-history PCA frame with much longer history than 1 year, conventional 1 year, to mitigate the finite-sample error. And as I said, this approach will combine a number of practical challenges. Okay, here's a summary. The first bullet point is related to the measurement issue. Okay. Basically, recognizing and addressing the secondary risk bias is crucial, but it's very difficult simply because we never know what the true covariance is in practice. It's known in simulation, but we never observe the true covariance matrix. So we need some proxy measure that is observable in practice. That's first issue. Second issue is more fundamentally in the theoretics, okay, in the sense that extending the covariance estimation to temporal domain may introduce a number of non-trivial challenges. For example, it requires a dynamic vector model approach instead of the static vector model approach, which must be much more complicated, and there must be a number of estimation issues. If we still want to rely on the PCA method, for example, one thing to be verified is the consistency of the principal estimates under the dynamic vector model approach. Okay. Third issue is also important, I think, is about the broad and narrow vector issues, in the sense that most of the stocks in the population are exposed to broad vectors like the market vector, the style vector. And the narrow vector, what I mean by the narrow vector here is that the vectors which impact only a small portion of them, like the industry vector or the state vector or the country vector in the European market. And it is well known that the presence of the narrow vector poses huge amount of challenges in detection and its consistent estimation. Again, in the context of the PCA estimation, principal component analysis blends the narrow vectors with the broad vectors to respect the mutual orthogonality constraints of the expected eigenvectors. So the more common terminology is a weak vector and a strong vector, in the sense that the stronger vector contains more portion of the broad vectors, and the weak vector contains more portion of the narrow vectors. But the thing is that even under the PCA context, detecting and estimating the weaker vectors is much more difficult. There are a number of potential inconsistency issues there.
Yeah.
Yeah.
Can I ask a
Sure.
question? We've also lately and completely, you won't find it written anywhere, have looked at these kinds of questions. And there are also broad weaker factors.
Maybe.
And there seem to be, they don't actually
Okay.
cause too much trouble, but I wonder if you've
I think
experimented.
it's a matter of the terminology issue, I think. The terminology of the strong versus weak, we follow the Baeho in 2023 paper that I'm going to introduce in a few minutes.
I see, okay.
So I know that there are a
I'm
variety of
just
the
thinking of
concepts.
like value.
Yes, right.
It's a broad factor and it's
But it's
much
weak.
less volatile than the market.
Compared to the market vector.
Yeah.
That's true. But what I'm saying is that, okay, at least in my talk, weak vector, I'm gonna use the two terminologies quite conceptually interchangeably between the weak vector and the narrow vector. At least
Okay,
within
yeah,
this.
so you don't have this blended thing. I don't
Yeah.
think it probably will affect. your
I'll get back to
results
that point in more
based
detail.
on-
in a few minutes.
Based on some little bit of experiments we've done, but they are,
Okay,
the market, right, the market thinks about them
sure,
is all.
definitely.
Definitely thinks a lot about those factors.
All right, anyways, according to these three major challenges, this is just one slide summary of our approaches and lessons, key takeaway as in my presentation. The first issue, again, is the estimation issue. For example, the estimation error, potentially measured by the distance between true and the estimated covariance matrix, it's not available in practice, we never know what the true covariance matrix is, right? So we need some approximator, which is observable. Maybe one naturally reasonable approach is constructing a minimum variance portfolio based on the constructed estimated covariance matrix. And we may take a look at its out-of-sample performance, such as the realized volatility. Okay, the idea here is that we expect to see that a more accurately estimated covariance matrix will achieve a smaller realized volatility of the minimum variance portfolio out-of-sample. It sounds reasonable, but the point is that our finding, one of our key findings, that it may not be always the case.
Right, so there are two papers that we looked at. I mean, Jose Manchero, who was here earlier this semester, said what you said now. There's a new paper we've been looking at. The first author is Bodner, some guy in Sweden. And they're arguing what you're arguing,
Okay,
that as a sample, I can send that paper over.
I'm very happy to
Yeah,
know that.
Pastor Bodner and somebody, and they're saying, you know, no, that's not always the best way.
I'll try to get to the more specific points later on. if you
Yeah,
permit, but
but there,
is that we may look at its relative measure to measure the potential discrepancy between the in-sample predicted volatility versus the out-of-sample realized volatility. Ideally, the discrepancy is 0, but in reality, the discrepancy becomes quite large, subject to the huge amount of the secondary spikes, for example. So that's usually statistically proxied by so-called bias statistics, which I will more carefully define in my talk. But anyways, the fundamental finding, the first lesson I want to highlight in this talk is that bias statistics can serve a more definitive and much better secondary risk measure than the realized volatility of the minimum variance portfolio if we try to proxy this type of distance.
this is like a bias statistic on an optimized portfolio.
Exactly right.
Yeah, okay.
Yeah. Second point, theoretical issue. The issue is that the risk factor structure may not be static over time, especially if we take a longer history. Okay, definitely. We may take two different alternative strategies. First strategy is more common in practice in some sense by focusing on just 1 or 2 years of median horizon under the static factor model structure and try to overcome the excess dispersion bias issue, finite-sample error issue to correct the bias. Okay, for example, like the GPS question, for example, we take different approach by taking a longer data history, and we try to address some potential instability or some inconsistent issues under the dynamic vector model. So we specify the model structure, the vector structure as a dynamic vector model. But our finding is that under the dynamic vector model approach, we still see, we show that PCA can still consistently estimate the covariance matrix and its inverse matrix under the large N, large T frame. But this statement is definitely subject to the mild regularity conditions. And we show that these regularity conditions are usually satisfied in the empirical data. But this regularity condition is actually one of the reasons why we cannot take like 20 years or 30 years. But empirically speaking, just extending the T to 5 or 6 years significantly reduce the amount of the secondary risk. That's what we show. Growth factor, narrow factor issue, the effector strength may not be homogeneous. And we further show that the performance of the long history PCA becomes even more pronounced in the presence of weak factors. It can better correct the potential issues in the presence of the narrow factors, which is also very important in practice. So this is more carefully stated our objective. We want to forecast the population covariance matrix and its inverse matrix of many stocks on a daily basis within the long history PCA framework. Under the dynamic vector model with potentially weak colonials across both the simulated data set and the empirical data set. Okay. Our first mission is to look for some observable proxy of the secondary risk bias measure. Okay. Again, this is an issue. We never know the true covariance matrix, but what we observe is estimated covariance matrix, which may be contaminated by the finite sample estimation errors. And again, what is known is that the finite sample estimation error in the context of the PCA-based vector model approach is to produce the excess dispersion bias in the estimated factor loss, especially when p is way smaller than n. And the problem becomes more serious, more pronounced in the presence of the weak vectors, typically narrow vectors. And as a result, the problem is the estimated medium variance portfolio is substantially more volatile than predicted. Okay. The issue is that, okay, if we mathematically represent the result of PCA, here W stands for the estimated factor loadings, estimated spectral loadings, and we focus on the terms in red, where the phi stands for the factor returns and the epsilon stands for the idiosyncratic return. By design, they are supposed to be uncorrelated, or at least very weakly correlated. But in the finite sample, this value is not zero, which causes the excess dispersion. Okay? As a result, estimated vector loadings of some stuff appear to be smaller than they actually are. In this case, the optimizer will certainly choose to increase their weights in the portfolio and vice versa, which causes the underestimation of the linear variance portfolio risk. And this problem becomes more serious, more pronounced in the presence of narrow factor, which is more difficult to be detected correctly. And in the relative sense, the relative contamination of the narrow factor is much greater, because by definition, the true factor exposure of the narrow factors are supposed to be very close to be zero for most of the stuff. So in the relative sense, in many cases, the excess dispersion bias causes nearly infinite relative error. So this is why usually the excess dispersion bias becomes more serious problem in the presence of the narrow factors. For notations, omega stands for true global minimum variance portfolio weights based on the true sigma covariance matrix, which is unobservable. And omega hat stands for the estimated global minimum variance portfolio weights based on the observable estimated covariance matrix. That means the true volatility of the true omega from the true sigma is unobservable. This is true minimum variance. But what we can observe is the last two. In-sample predicted volatility of the omega hat calculated from the estimated covariance matrix sigma hat, and the actual, which is the to be realized volatility of the omega hat, that will be realized from the actual true covariance matrix. Those two are actually observable. We try to focus on the potential deviation between the two. And for a better understanding of, okay.
The last one, you have a true covariance. Oh, I see. And you're saying that what's realized
Exactly.
is some proxy for the actual.
So this is sigma is volatility function
Yeah.
or the estimated.
It's realized volatility of the estimated portfolio.
Exactly right. So
Yeah.
in the statistical sense, we can proxy this as a realized portfolio.
And this is a one constraint portfolio.
Yes, right.
Okay.
Unconstrained portfolio without any
One
short term.
one constraint, you're
Okay.
fully invested,
Exactly.
single
Right.
constraint portfolio.
Yes, and we don't specify the short selling constraints here.
Uh-huh.
So by solving the optimization problem in the form of the quadratic programming, we obtain the closed solution for the true omega and the true variance in this form, which are completely specified by the true precision matrices. Okay? And the estimated minimum variance portfolio omega hat and its predicted in-sample predicted variance can be expressed in the same form by simply replacing the true precision matrix to the estimated precision matrix. And as I highlighted, the mechanism of the excess dispersion bias is that the predictable, the stylized fact is that the finite sample estimation error in the estimated precision matrix typically underpredicts the predicted volatility. Okay, and we define the epsilon as the estimation error of the precision matrix. Then we can express the predicted volatility of omega hat in this form, where the first term, the denominator, is exactly the same as the denominator in the true volatility of minimum volume. And the thing is that the second term here, the error term, as a second term, the denominator typically increases as the error estimation error increases. This is the source of the excess dispersion bias, which causes the under prediction of the predicted volatility. If we define the volatility ratio as the out of sample volatility of the omega hat divided by the in-sample predicted volatility of omega hat, by doing some math, we can actually derive that this expression can be expressed in this form, where the error term in the numerator is double the error term in the denominator. And this approximation makes some sense when this term in the second order of the epsilon is negligible. This is what we use to observe, in the sense that as the size of estimation error gets larger, this volatility ratio is monotone increasing function. Okay. But by definition of the volatility ratio, the numerator, the actual volatility, which will be processed by the realized volatility itself, can be expressed as the product of the predicted volatility and the volatility ratio. And as I highlighted, the typical problem in practice is that this predicted volatility becomes under predicted. So it becomes smaller as the error increases, while this volatility ratio is increasing as the error increases. So as a result, this realized volatility may not have a relationship in some area. Okay. To highlight this issue, we perform a very simple numerical experiment to illustrate this point. Here we assume that there are 2,000 stocks in the market with 5 uncorrelated factors, and we first construct the true covariance matrix by drawing a true factor loadings from a normal distribution with some true dispersion theta 0. And then we also construct the estimated covariance matrix sigma hat, which is essentially concatenated by adding some exit dispersion parameterized by theta. Okay. So what we want to do is to calculate some candidate error metrics across various thetas. So first, we focus on the ideal measure, error measure. Okay, I hope you can see that. So left panel shows the degree of the covariance matrix error measured by the average Frobenius norm between true and the estimated covariance matrix across different values of the exit dispersion in simulation. Okay, as you can see, it's increasing function, okay, in a non-linear way. And also in the right panel, we do the same thing with the precision matrix error. It's also monotone increasing, but what we observe is that in the metric of precision matrix error, this error metric is more sensitively increasing in the small amount of the error. So when we try to run the say horse racing among the pretty good horses, okay, to compare the performance of some benchmark estimation methods, this measure is going to be more sensitive and more definitive to measure the accuracy of the estimation error. But the thing is that this measure is only available in simulations, so we need some proxy. The next slide, I'm going to compare the performance of our ideal secondary risk bias measured by the precision error measure based on Frobenius norm versus the volatility ratio, okay, which is the ratio between the actual volatility and the in-sample predicted volatility of the minimum-variance portfolio. Our observation is that, as expected, the ideal value 1 is achieved when the exit dispersion is 0, and it's increasing, monotone increasing, and its increasing pattern is quite similar to our ideal secondary risk bias measure, which is not available in the empirical study. However, when we turn to the actual volatility part, okay, in the right panel, okay, this is the pattern of the actual volatility normalized by the true volatility. This normalization is just for highlighting that the ideal value is 1. So when we apply the realized volatility across different methodologies on the same data set, the true volatility will be applied in common. So anyways, if we take a look at the realized volatility pattern, it should be something like this. The point is that it may not have a monotone increasing pattern across all of the horizon. So especially there exists some kind of saddle points. So it may, if we just compare the performance of the different approaches based on the realized volatility, it may be misleading subsets potentially. And also, it may be more noisy matrix indicated by the confidence interval, the width of the confidence interval compared to the volatility ratio.
Sorry, Dan, can you remind me, how you simulated the data?
Okay. So this is just for the measurement, to deal with the measurement issue.
Yeah, but
we
you
don't
made
apply
this
the
graph.
PCA.
You made a graph with some
Right.
simulation, maybe.
So there is a true dispersion from the theta 0, which is fixed. So if we specify the factor model with a true dispersion parameter value, we can we can construct the true covariance matrix based on the
Is it like a multi-factor model?
five-factor model.
A five, that's what I'm trying to say. You have five factors.
Exactly,
Yeah,
five-factor.
sorry, that's so much to
Yes.
come back to.
So we first wrote the true factor logs, okay, to construct a true covariance
True
matrix.
factor loadings are going from the normal distribution.
Some prefixed true dispersion parameter,
Yeah,
okay, which is empirically motivated. And now this beta is a key parameter which parameterizes the degree of the excess dispersion, which is the source of the finite-sample error, maybe. Okay?
some of these are narrow factors.
No, in this simulation,
In this
there's no.
simulation,
Okay,
you made up five factors. They did them all the same way.
exactly.
Drew the things from a mean one and variance, something or other. Okay,
Right.
got
So
it. Okay.
as we increase the excess dispersion parameter,
Mhm.
we see how the some of different error metrics behave. Okay?
That's good, right? The
Mhm.
Frobenius
So
norm.
we think that this can be one of our ideal secondary risk bias, but this is certainly unavailable in the empirical study because we never know the true
Mhm.
precision matrix. And we argue that this volatility ratio can be a good proxy for this one in terms of its shape and monotone increasing pattern with relatively narrower confidence interval, of course, 1,000 different simulation seeds compared to the actual volatility. Okay?
Yeah, there's a, certainly a trade-off that I often worry about. You could get even if you get the risk forecast right, portfolio could still be the very wrong portfolio.
Exactly. So practically speaking, maybe it's another different problem. Okay, maybe it is valid to try to construct the minimum variance portfolio which achieves the minimum realized portfolio, minimum variance portfolio. That's different question. But if we try to measure something like this in empirical study, my argument is that instead of the actual volatility, the volatility ratio, looking at the volatility ratio, provides us a better sense.
Well, of something,
Something.
right? Suppose that you're using your covariance matrix for two things,
Right,
to construct and to measure.
right,
And suppose you find a way to construct better that you can forecast risk more accurately, you could still be very far from something that's actually minimizing variance given the constraint that you
Right.
have.
Right.
Which, I mean, that's fine to do, but that's not taken care of here. This is just one aspect. of the
this is
problem.
only for the measurement.
So this is for forgetting something you can measure well.
You just mentioned a very important point. We construct the minimum variance portfolio here, not to minimize the realized volatility.
Right, but to
But
get the-
to have some measure, some observable measures of the secondary
So
response.
one thing that you can do is take like an equally weighted portfolio, which is pretty easy
Mhm.
to forecast risk for compared to other things. But it tends to be much more volatile. It's not, you would have to have a very special world in which that was the true minimum variance portfolio, and we're not usually there.
You're right. We did that in previous studies, but again, one of the reasons why we focus on the minimum variance portfolio here is that it's the most sensitive portfolio to the potential estimation error. Yeah, in this matrix, of course. So this is to motivate our empirical study setup.
Well, but there are cases when the equal weighted portfolio is the minimum variance. portfolio.
That's
Make
what I'm saying, exactly.
Make
So-
one up right now. It's just not the usual state of the world.
Okay, you're kind of jumping ahead. Okay,
Oh,
so we
okay.
had a question, what's actually happening around here?
Yeah, good
Okay?
question.
Yes, so this is something we call kind of illusion of the actual variance. So
Uh-huh.
suppose that we are really bad in the sense that our estimation result is certainly different from the true covariance matrix. But suppose that the product of the true covariance matrix and the estimated precision matrix, this matrix has an eigenvector close to the vector of ones. Suppose that this happens. This eigenvector doesn't have to be the leading eigenvector, but one of the possibilities is that suppose that we are in the very normal calm period and the true dispersion of the market betas are not that significant. And we are really bad at estimating the covariance matrix, so maybe we shrink too much towards the identity matrix, okay? And this certainly happens, right? This certainly happens. I mean, the eigenvector of this product matrix is very close to the vector response. But if this condition is satisfied, what happens is that the actual variance of the estimated minimum variance portfolio turns out to be very close to the variance of the true global minimum variance portfolio. So this is something like that. But even if this approximation is not exact, still this point may be generating some non-monthly pattern in some area, especially very important area when the error is quite small.
Yeah, that's a very interesting feature.
Yes.
So there's a lot known about when sample eigenvector, say, in single factor models is a consistent estimator
Mhm.
of the truth,
Yes.
for example, and then so if you take like I don't know if you're familiar with the Johnstone 2001 paper, I can send you if you don't know it. The original spiked model, although it's not that spiked, if the eigenvalues stay bounded as they do not in our case, but they do in his case, and P and N grow to infinity in proportion, then everything's
Relatively steady.
inconsistent.
Okay.
But if the eigenvalues grow, as they do in our case, and P and N go to infinity, then the leading eigenvector is the consistent estimator.
I see.
So now if you have a big gap between the number of securities and the number of observations, then the leading eigenvector is always inconsistent. So maybe you don't get close to these cases. So it really kind of depends on, well, those are asymptotic theories, and even if you're in a consistent one, how large you have to be to have that.
I see. So
Does affect.
actually, the next section is about the theoretical analysis about the consistency of the PCA estimator. So maybe we can discuss more on the.
And by the way, everything I just said about Johnstone is true only under Gaussian assumptions. So reading them, you have to have a real love
Yeah.
of spaghetti to read this literature, very fragmented.
Okay.
But there's a lot known about when that thing might crop up that you just said,
Okay.
and
Great.
a lot of unknown.
Okay, we can continue our discussion with the punch.
Yeah.
Maybe this is quick summary. So we highlight that in this framework, if we want to proxy something like this in the empirical study, my argument is that the bias statistics is a good statistical proxy for the volatility ratio, which is a proxy for this error. On the other hand, the realized volatility or the actual volatility may be potentially misleading in some sense. And okay. Maybe I have to quickly cover this theoretical part, but this part is to justify the use of the PCA in the longer history of the data set by addressing these two research questions. The first research question we try to address is that under the large N and large T framework, instead of the large N and big T framework, can PCA be a consistent method for estimating dynamic vector model? And our answer is yes, of course, under some reasonably mild assumptions, and our dynamic vector model of structure specification and the assumptions are mostly coming from this reference paper written by Brandon Bass and his co-authors, including
No, I don't know that one. Please send it to me.
Okay, I'll definitely send it. But anyways, our assumptions and the model specifications are mostly coming from this paper, but there's one big difference. This paper is completely silent about the existence of the big vector issues. So they simply assume that all of the vectors are strong vectors. So it is related to our second question. Okay, does the LH-PCA approach output from the variance of the traditional PCA method with the median history of the data PM and mitigate the secondary risk bias in the presence of both strong and weak vectors? Our answer is yes, and I'm gonna show you our simulation study and the empirical findings. But anyways, all of the assumptions related to the weak vector model is coming from this reference paper written by Baeho in 2023. So our approach at the modeling stage is kind of the combination of the two reference papers. So here's one page summary of our theoretical analysis. We theoretically show that the LH-PCA can consistently estimate vector loadings under the dynamic vector models specified by those two reference papers in the presence of the weak vector issue. And we further demonstrate, which will be focused on the rest of my presentation, in simulation the empirical study that the LH-PCA significantly, substantially mitigates the secondary risk bias in some sense, based on the measure I just introduced. So this is a quick a summary of our main theorem, okay? Here, sigma n is the true covariance matrix generated by the dynamic vector model. And here, sigma bar is approximated static version of the covariance matrix. And we show that under the large n, large t framework by letting those two parameters be infinite. Under the average Frobenius norm metric, okay, those two covariance matrices will converge, and the converging speed of convergence is determined by the linear between n and t. So when we deal with the large n extending t, it's definitely helpful. And the same convergence rate is achieved for convergence of two preceding matrices as well. Okay, yeah. And it further justifies the use of the LH-PCA for estimating the static part of vector loading, which is actually in the model, we specify the vector loadings are time varying. But here, what I mean by X bar is kind of the mean reverting level for the stationary value. It's a static approximation of the vector loading. We can definitely consistently estimate this vector loading part, baseline vector loading we call by the LH-PCA, and its convergence rate is also specified by n and t in some sense. So extended t is quite useful when we deal with the large n. So let me turn to the simulation study, which is more realistically specified. So we try to mimic the European data set here. But the beauty of the simulation study is that we know everything in terms of true structure, so that we can compute the true covariance matrix here. So in our simulation study, we specified that there are 2,000 stocks in the market. And we assume that there are 31 factors in total, 4 broad and 27 narrow factors, including 11 industry factors and 16 country factors. This is the true factor structure in our simulation study. And we employ variable volatility factor structure by adapting the two region, macro regions between the normal region versus crisis region. And in the crisis region, the volatility, the factor volatilities are multiplied by some, some constants like 1. And also, we employ the time varying factor loading dynamics in the true model specification to address the dynamic nature of the vector structure based on the mean reverting alternate limit process of the true vector test. Okay. So we have two sources of the dynamics, one from the macro region switching volatility factor structure, and the other one from the time varying factor loading dynamics. And we still institute the two history scheme. The first stage, we use the LH-PCA with 6 years, 1,500 days to back out the expected dynamic factors. And then we employ the responsive covariance adjustment. It's measured based on the average with the conventionally used 40 days of temporal. So this is 2-stage.
Can I ask a question about, I'm not familiar with these models. So when you have something mean reverting factor loading dynamics.
Yes. So
This is a question. So mean reverting suggests that the factor loadings come back to some mean.
exactly. This is some long run mean of the beta I.
So that's a 2,000 vector there. And there's some long run mean of the 2,000
That's correct.
vector.
That's correct. In this simulation
Okay.
study.
I
Yes.
see it.
So we know what's going to happen in terms of the true covariance matrix tomorrow. And we try to use the past 1,500 days of the simulated return to estimate the factor loadings and to estimate the
Got it.
covariance matrix and preceding matrix as well. Yeah. So let me skip the more details. So basically, in our simulation study and the empirical study, we basically compare the performance of the 4 benchmark estimation methodologies. LW stands for the Lewis shrinkage estimator of the sample covariance matrix. So here, LW doesn't use the vector model. It just uses the sample covariance matrix and we apply their shrinkage estimator.
So remind me which, so I recently learned that early in the 2000s, Ladwell will
So this
run
is
toward 3 things.
2004 version.
So there's one toward a constant correlation matrix, one toward a single index, and one toward something else, I don't remember. What's the
I
target?
believe that the target here is the identity matrix.
The identity matrix.
Yes.
Okay, so that's effectively like an eigenvalue shrinkage.
In some sense, yes.
Yeah,
You're right.
okay.
I think you're right.
Okay, the
Anyways.
other ones aren't. The other ones are different.
The rest 3 are based on the spectrum model approach. And the PCA means the typical PCA method based on just 1 year history of the data.
Uh-huh, when you,
Okay, 1 year PCA.
and how many factors do you pull out when you? do it?
Oh, that's a good question. Actually, in terms of the determination of the number of eigenvectors to extract,
Uh-huh.
we rely on the estimator suggested by the Baeho in 2002.
So they tell you how many factors?
Exactly right. But one issue is that in the 2002 version, they were not actually, their paper is also silent about the narrow factor issues. But recently, okay, I should mention this one. I think that this approach is kind of conservative setup in a sense. But anyways, recently, last year, corollary 2 of Uematsu and Yamagata, I think they are Japanese, but they show that by the 2000 estimators remain still valid for determining the number of relevant eigenvectors, where the principal component estimates of the vectors are still consistent with the potentially variable weak vector levels. They do discuss the weak vector issue as well. So we employ this method.
Two more questions.
Sure.
What's the approximate number of factors that the spying estimators?
So
give you?
we
Like-
basically use, okay, in the simulation study, we just generated 1500 days.
Yeah,
But in the empirical study, we use the moving window.
yeah,
So
that's
in,
fine.
in each window, we try to extract the number of factors to extract.
See, but you started with 27. Does the estimator tell you?
This is the true.
The truth. So does the estimator tell you 27 or 10? What does it tell you?
It's the number of eigenvectors. This is the true vector.
Yeah, yeah. So what?
The eigenvectors usually is around 5 to 7.
Uh-huh, okay,
But it
that makes
depends on-
total sense.
Exactly right.
Doesn't not surprise me.
Okay.
Just
Yeah.
wanted-
In the empirical study, it's true. It's the same, around
Oh.
5 to 7, depending on the time though. So anyways, here the left panel is based on the ideal metric, based on calculated under the average Frobenius norm. We can calculate this metric because this is a simulation, okay? And here y-axis is represented in the log scale. And in the right panel, we calculated the metrics under the volatility ratio, which can be observable in.
Yeah. But I can't see the colors.
Yes, that's the point. Okay. First observation is that, we should use the vector model approach because vector model approach is way better than the Ludo angle, at least in our simulation study. It's about 10 times better.
The first one is the one I can see
Exactly.
the
It's
colors.
the order. I mean,
Oh,
in
the
next-
order is right, okay.
Exactly right. So yeah, you're right. Since the y-axis is represented in the log scale, they're kind of crumpled, okay?
Yeah,
But the next slide, I'm gonna zoom in those two plots to focus on the relative performances on the rest 3 vector-based models. Now the y-axis is in linear scale.
Mhm.
So left panel is based on the ideal secondary bias, and the right panel is our observable proxy. First observation is that using longer history of the data for the PCA estimation certainly helps, and the difference is statistically significant than the other 2 ability.
so when you did that middle one, which I'm familiar with, how many factors did you pull there?
Again, we use the number of
You
factors.
used the number and you corrected one.
You correct one, what do you mean?
Well, if you're using a GPS correction, are you correcting all the factors?
Oh,
You're
yes,
Correcting one of the
definitely.
factors, what are you?
These simply follow the directions in the paper.
But in that paper, it only ever talked about one factor, so you had to decide to do something with the other factors, which we didn't tell you what to do.
So we just corrected the leading eigenvector.
You corrected one factor.
Exactly
Got it. Okay, that was my question.
So I think that some research is going on under the multi-factor version of the GPS, but we are not familiar with that.
It isn't out yet.
Yeah.
I can tell you
Anyways,
what it
yeah.
says, but anyway, I just
This is
wanted
the
to know. what
fraction
you
of
did.
the leading eigenvector.
You found however many factors there were and you corrected one. Okay.
And the first 2 methods are based on the 1 year history.
Uh-huh,
This is based on the 6-year history.
uh-huh.
And my understanding is that the GPS correction is not designed to mitigate the error under this metric, but it should work something under this metric, right?
That's true, and it also wouldn't mitigate the error much under a longer history, because it works when the number of securities is a lot bigger than the number of.
I think the beauty of these two, GPS and our methodology, is that they can be merged. in practice. I mean, we can even think of it, say, LH-GPS method, because this is simple PCA version, simply extending the T to 6 years.
But if you do the efficacy, well, we can talk
Exactly.
about.
Our
the
contribution of the
efficacy
GPS
as it
may
goes
be
down.
smaller,
Yeah,
of course.
yeah.
But anyways, we should deal with finite N and finite T in practice anyway. So there should be some room to make some contributions in both methodologies. Anyways, this is our first observation.
Uh-huh.
But when we focus on the annualized, I mean, the actual volatility or the realized volatility in some sense, okay, this is again 4 or 6 scores very simple. Okay. Still, we can see that the Ludwig is way worse than the other vector-based models, but see the differences. On the right-hand side, on the right panel, the y-axis is now in the linear scale. That means the difference becomes much narrower. And especially when we focus on the rest of the 3, the order is reversed. Potentially because of the kind of settle point I highlighted again, non-monotone pattern. And moreover, the difference becomes much less statistically significant. For example, PCA and GPS, their mean level is around 7.35% in annualized term, and the LH-PCA is 7.45% per annum. So the difference is 0.1% in this simulation study.
Got one more question. Your simulation was with Gaussian data?
In simulation, yes.
Okay.
We are within this Gaussian distribution. Yes, that's another good point.
Well, right, that's a very reasonable thing to do. I just want.
But in the empirical study, we should not say that.
Well, it's not very
It's
Gaussian.
not that we can do. So our ultimate goal is to show that the long history PCA method is also working in the empirical data. The source, we have 2 sources of the data sets for our empirical study. One is from CRISP for the United States stock market, US stock market. And the other one is the Campus Global for the European stock market. Okay. Also, the period is the last 21 years until the 2021. And for the implementation of the long history PCA, we consider overlapping 6-year windows to ensure that we have 1,500 days, present days in each window, and this kind of moving window, overlapping moving window approach. So on average, in each window, in case the first data set, we have over 2,000, and also in the European data set, we also have on average, 2,500 stocks. We try to mitigate the potential survivorship bias issues by addressing some realistic issues here. And the confidence intervals can be approximated by bootstrapping samples of the Z-score.
So what's the universe for these again? Sorry,
So universe, okay, for the US stock market is the CRISP data set. And the source of the European data is Campus Global.
So you're using US and Europe data, no
Yeah, so
Asian
we
data,
have 2 different sources of the data set.
and you're using daily data.
Daily data.
Do you have any worry about time zones?
In the
Oh, they're separate. You're not mixing them. Okay.
Yeah, right. So the issue here is that we don't have the ideal measure any longer. We never know what the true covariance matrix is. We
Right.
simply rely on the proxy measures. The first proxy measure is the bias statistics. Okay. And the left panel shows the results based on from the first data set, and right panel shows the result from the European data set. Similar pattern, the sense that the Ludwig correction of the sample covariance matrix produces much worse result than the vector-based model. But when we try to focus on the performances of lab 3 in the linear Y scale,
Yeah.
similar pattern, I think, from the simulation study. Okay, so still using the longer history of the data set is very helpful to make
More
better
accurate.
bias statistics,
Right.
but there's still some room because our study period is over the last 21 years, which includes finished crisis period and the COVID-19 period. And I believe that most of the room left is coming from those crisis periods, which is not surprising. But anyways, one of the potential caveat pitfall implied in the bias statistics is that it may be contaminated by potential time resolution effect in the sense that if there's some cyclical, performance effects in the realized Z-scores, then the overestimated period may cancel out the performance of the underestimated period. So maybe one of the way to correct that kind of potential bias is to focus on the mean rolling absolute deviation. Okay, maybe I can. Okay. I thought I skipped that slide. Okay, where is it? Simulation study? Okay. So, anyways, the idea is that the MRAT and the Q statistics, those two measures are variants of the bias statistics in the sense that they both penalize both the underestimated result and the overestimated result. But anyways, the smaller the MRAT, the better, definitely. So similar results. We focus on the three last approaches, LH-PCA performs best. And similar results we can observe from the Q statistics. When the returns are normally distributed, I believe the ideal value of the expected Q statistics is about 2.27 something.
Yeah, something like that.
Right, but definitely empirical data doesn't obey the Gaussian distribution assumption, so it may be different. But anyways, if we're concerned about the potential under-prediction of the incentive predicted minimum-variance portfolio's variance, definitely the lower, the better. But the next slide is one of the most highlighted, the point that I want to highlight in this talk. If we take a look at the real life volatility, okay, the pattern is totally different.
I was gonna just ask that question.
Yes, sure. So let me first explain what we observed and our interpretation first. Left panel shows the result of the out of sample realized volatility coming from the CRIS data set, US market.
Interesting.
Yes, based on the estimated minimum variance performance. Okay.
Yeah,
So the best performance was shown by the LH-PCA, and it's slightly different from the GPS, and followed by the LH-PCA. What is even more striking is the result from the European data set, in the sense that Ludwig correction, the shrinkage estimator of the sample covariance matrix, produces the smallest real-life volatility.
it's like, what is that number? I can't do 1.7.
1.7, yes, it's like,
Really tiny. What,
Right,
and
that
how many
means-
stocks in these two universes?
so it depends on the moving windows, but on average in the European,
They're very similar.
right, very similar. So
Uh-huh.
it shows that if we didn't make huge amount of mistake here, the European data set, European stock market
Uh-huh.
can enjoy much stronger power of diversification issue, right? I mean, usually, okay, this is our guess, okay? We never know what's actually happening, but maybe the true market betas in the European stock market is less dispersed, and the Ludwig shrinkage method may work in this sense. What I'm saying is that what Ludwig shrinkage estimation method is doing is that it shrinks towards the identity matrix as a target.
Yeah,
So as I said, if the true covariance matrix has leading eigenvectors, something close to vector of ones, maybe, the market betas are known to be less dispersed during the normal times than crisis periods.
that's.
Usually, it's empirical.
Not always.
Not always, but there are some empirical papers to report that kind of
Yeah,
patterns.
yeah.
But anyways, let me correct my statement. If the true market betas are less dispersed in the European market than the US stock market,
Yeah,
and if we shrink a lot so that the estimated covariance matrix looks like the identity matrix, then Ludwig estimation method will produce very nice realized volatility results out of sample. If our goal is to achieve that, or to achieve the maximum Sharpe ratio, which we realize out of sample, then Ludwig estimation method it is very nice. But in our sense, according to the purpose of our study, to accurately measure this kind of error, if we define the secondary risk measure like this, then Ludwig is not a good idea, because it shows, consistently shows that a vector-based model produces much smaller bias statistics and is variance.
certainly. Have you looked, just at a measure that I would add to this? Have you looked at the leverage ratios these portfolios are constructing?
Uh,
It's kind of telling,
Okay,
because,
Could you be more specific on what it is?
yeah, because and also, there's two great old papers that certainly Lenoir and Wolf spent a lot of time reading. I should read their early papers that have nothing really to do with estimation error formally, but they do. One of them is by Green and Holyfield, and one of them is by Jagannath and Vaughn. And they talk, both papers, well, Jagannath and I talk about estimation error. Green and Holyfield don't, but they talk about how extremes in exposures generate extreme weights
Oh, I see.
in these portfolios. So, I mean, this is all, I think, great, and I've learned a lot listening, and hope we can continue talking. But at some point, you want to consider investability,
Mhm.
and there, all of your portfolios are probably levered. Very rarely is a true minimum variance
Right.
portfolio unlevered, and if you look at the way the leverage ratio varies over time, or at least when we do in some analogous, if not similar studies. It spikes, it comes down, it's kind of a wild number. And then you can also look at like a Herfindahl index on the thing and see how, is this like one long stock and one short stock and a lot of cancellation. And while the results are certainly interesting, even in those cases, you want to know if they're being driven by those cases or by
I
something
believe
else.
it's another very exciting research topic. Yeah. So
Those
maybe
things
we
really
can
do.
still apply a similar approach and take a look at this result based on different metrics or for the different problems.
Right, just for the usability, I mean, all of
Right.
these things lead to nice theories. But if you're trying to get at something that someone can actually use, these other metrics totally matter.
Of course. So I have
Turnovers and another
one
one.
last slide.
Yeah.
So
Yeah, that's great.
So the message is quite clear, I think. If we focus on the objective to minimize something like this, in
Uh-huh.
terms of to mitigate the estimation error of the precision matrix, using longer history is definitely beneficial. Okay, maybe up to 5 to 6 years of history. So we first observed that in terms of the measurement issue, bias statistics are a better proxy for this error metric than the real-life volatility. And we showed that the long-history PCA method can consistently estimate the covariance matrix and the precision matrix under dynamic vector structure. Okay, we have some theoretical justification. We show some simulation evidence, and we also empirical evidence from the 2D data sets. But still, there are some future research topics left, I think. As I said, like the LH-PCA still needs some room for further improvements. For example, it may be ideal to let the data speak about the optimal choice of PL by the key data. We have some sensitivity analysis result, but this is something we need to dig into maybe. And also, as I said, we may combine some other potential correction methods on top of the long history PCA method. If we want to focus on the weak vector issues, maybe some machine learning techniques like, for example, sparse dictionary learning better estimate the weak vector issues. And even more generally speaking, we may extend the scope of the research into the asset pricing implications by examining the vector prices, especially for the bigger vector. Maybe I hope that my guess is that using longer history data, but then we can help in this dimension as well. But it's still our future research topic. Yes, so this is all I prepared for my presentation today. Thank you very much. If you have any further questions.
Yeah, anyone have any questions, including those of you not muted on the web?
I'm happy to share this slide, and we are currently we are under the process of writing up the draft for the details.
Yeah, I'd love to see it when you
I'm
get
happy to
it.
circulate the draft once it's completed under, for example, CDAR working paper. Hopefully,
You'd be great.
so I'm happy to share.
Questions? Comments? I have a ton more, but
Sure.
we're gonna get kicked out of here. Well, thank you.
Okay, thank you very much.
Next week, that's really great. Okay. Is the final, CDAR seminar of the semester. Nick Gunther will be presenting, in person, right, Nick?
Do my best, yes.
Good, so we'll see you in a week.
That's the
And,
plan.
Thank you, Baeho.